Let's go quickly to the MySQL replication to show you that even though it's MySQL, this is not a Galera cluster. So we don't have the flow control overview here. And we only show the applicable interfaces to you, because otherwise it would just confuse you. Why would I have, for instance, Galera overviews in a MySQL master-slave cluster? Furthermore, everything is almost equal to the other MySQL flavor. There aren't that many differences, except when you go to the nodes and we're going to manage the master. You cannot do any operations that are supposed to be done on a Galera cluster. Actually, the reverse is can be seen here with a replica. So the slave node, we can actually promote this slave to become the new master. We can stop the slave, or we can tell it to copy all the data from the master again and start slaving from there. So we can reinitialize this particular slave. Also, if we have multiple slaves available and we would promote this slave to become the new master, all the other slaves will start slaving from this new master, obviously. Similarly, for MongoDB, we only show everything that is applicable to MongoDB. The dashboard is slightly different because MongoDB has nothing much in common with MySQL, so we show the ops counters here. And you can define your own dashboards here. So you would be able to add new dashboards and easily add, for instance, the index stats of a certain schema within MongoDB. Node management is similar. So we try to keep our interface looking almost similar to what you're used to within, for instance, Galera or MySQL or Postgres. Another interesting thing to mention is our user management. User management allows you to create organizations, and organizations can be, for instance, either a real organization, so you can do a bit more like hosting environment, but you could also use organizations as a team, so you could add multiple teams. It allows you to create access control based on roles. So we have the role admin by default and the role user, but you can define your own role. So, for instance, we have a developer. And this developer role, we want to deny access, for instance, to do anything with jobs or clone a server. But allow them to look in the overview. And that basically would change the developer once he logs in to only be able to do certain tasks within within ClusterControl. And the third thing that is interesting is LDAP access. We support LDAP to be used within ClusterControl, and the beauty of this is you can either integrate it with your existing Active Directory or Open LDAP solution. So if your company is already using LDAP for centralized authentication, this is really nice to integrate it within your organization. Or if you're a hosting company, you can use LDAP to sync your user accounts into ClusterControl and have the organizations synced into this interface. That's about all about the things we wanted to show on ClusterControl. Oh, there's one more thing I wanted to show, that actually you can add, for instance, an extra node into clusters. Because I spoke about the three pillars, and I think we covered already three of the four. So the last pillar is scaling, so we can scale our cluster. And in case of Galera, we add nodes quite easily. We can just add another one. and immediately once I press add node, a job will respond and it will be synced into the cluster. Similar for master-slave replication, we can add nodes quite easily this way. So we can add, for instance, 1, 2, 3, 4 read slaves and be able to scale it that way. And for Mongo, we just add a new node to the replica set. This is a sharded cluster. It will automatically be added to the cluster, and it will immediately receive traffic from the remainder of the cluster. So I'll hand it back to Andrew now. Thank you for watching the demo.
Thank you, Art. We continue with CloudStats. Art showed you how ClusterControl works, that you are able to add MySQL Galera clusters to ClusterControl, master-slave replicated cluster, as well as Mongo and Postgre clusters with ease. And of course, if you think about the past days when we had no graphic interface to those, it was a nightmare to manage. And right now, as you can see on this slide, where we actually divided the data into 2 different database types, we are hosting the large amount of data in a NoSQL cluster in MongoDB managed by ClusterControl, as well as we're hosting a Galera MariaDB cluster, which contains customer data, billing information, accounts, and everything. And the reason for this is that actually in the Galera cluster, the data gets replicated the number of times as the number of nodes that you have. And for example, if you have 5 nodes, the data will be replicated 5 times. And add to that the RAID disk setups that you already have that are already replicating the data 2 times. So we found there was no specific need for us to replicate a large amount of data several times. So for example, we have in a MongoDB cluster, we have around 5 terabytes of data now. So if we had 5 Galera nodes, each having around 5 terabytes of data, it would be extremely difficult for us to manage those, and it would require 5 times the storage that would be required to store everything. So we're actually right now running everything on SSD drives for the application servers and the Galera cluster because it allows us to have a high input-output rate on the disks IOPS. And MongoDB clusters are not that IO hungry, so we can run them on cheaper SATA, SAS drives, and which are also larger. So you don't need to, if you have a large amount of data, you can distribute the data across different types of storages. And the good thing, of course, is that they both can be managed by ClusterControl. And from a unified control panel, you can see what's happening with both of your clusters. And even more, you can add any number of clusters to it. So it's extremely convenient, and that's why we chose the ClusterControl for the management of our data structure. So the current architecture after we implemented the ClusterControl and clusters looks like this. So we have application servers which are load balanced in front of them, and they are receiving the traffic from server reports, visitors, etc. So we're load balancing traffic across those. And then we have 2 database clusters which are linked to every single application server through HAProxy, which performs load balancing separately for each cluster. Of course, it performs load balancing for MariaDB cluster separately, and the MongoDB cluster is connected to the application servers as well. Each of the node in a cluster represents a dedicated server run by VU servers, and each node is connected via a real network, via a private network, so no data is exposed to the public. And this architecture allows us to have a write scalability, allowing to scale both clusters and add nodes as necessary into Mongo cluster and into MariaDB cluster easily with the ClusterControl panel. So also MariaDB cluster is stored on SSD drives, as I mentioned, and the MongoDB is stored on the SATA drives. And this architecture allows us to have a complete failover in case of failure, either on the application server side, or on the MariaDB database side, or on the MongoDB side. So this structure allows you to have high availability, failover setup that normally would let you have a lot of traffic, and we're expecting the application to boom in the next several months. So this will allow us to scale the application easily. But of course, some of you will wonder if the storage choice and why we decided to store it on local SSD drives. This is the IOPS benchmark of various public clouds like Amazon, Amazon AWS, Microsoft Azure. And the problem with those is, of course, that they have storage. The storage is not really local. It's attached to the server via network. And the network storage is divided across many tenants and shared by a lot of clients. And there is simply not enough IOPS for every single client. So Microsoft Azure, for example, limits IOPS per disk up to 500 IOPS for standard disks and higher for premium disks. And you, on Azure, for example, you have to create a RAID setup on your virtual machine to have a higher number of IOPS. And as you can see, the Azure like this. So Azure is currently having, according to our benchmarks, showing around 16,000 read operations per second. So and 15,900 write operations. So the Amazon is actually performing slightly better. The M3 X large showed a higher number of writes actually than reads. That was quite unexpected. And you can use your own disk system to test for the number IOPS. And for us, for example, having a high number of writes was important. That's why we implemented storage on our local SSD drives at VU servers instead of private clouds, although some may offer greater flexibility, but local SSD storage has a much higher amount of IOPS. Reads went to 250,000 and writes are at around 100K. So it's actually up to you. Some applications may be okay with lower IOPS rates in Azure or in Amazon AWS, but the application gets larger, it will require you to have local storage disks, and that's what we encountered. And we found that MariaDB was quite I/O hungry, so we had to store it in-house on our servers, on our network, instead of choosing a more flexible and sometimes even more expensive cloud provider like Microsoft or Amazon.